moving from glucose 6-phosphate to fructose 6-phosphate. That's the second reaction. But I want to give you a little more detail on that as well. Let me put up glucose. Oxygen linked, this is off the record by the way, you don't need to remember it, but just information. Oxygen linked to the number 1 carbon. Now for fructose, which would be over here, again I'm ignoring the phosphate because right now I don't care. Fructose, that same oxygen is linking to the number 2 carbon. See, there's a number 1 up there. This is number 2. So coming back here, what's being done to convert glucose into fructose is you break the bond between oxygen and the number 1 carbon, break the bond, move that bond down to number 2. So in other words, coming here, this is glucose right now, but if I break that bond between oxygen and number 1 and move it down there, that's now fructose. See, there's your number 1 carbon. If you kind of move it around a little, this will be that up there. There's your number 1 oxygen linking to number 2, 3, 4, 5, and 6 up there. So the only difference between glucose and fructose is which carbon is the oxygen linking to. If oxygen links to the number 1 carbon, we have glucose. If oxygen links to the number 2 carbon, we have fructose.
I didn't understand that.
What? Okay. So again, glucose and fructose are really very similar in structure. There's not that big a difference, even though they look completely different. But here's oxygen linked to number 1 carbon. There's number 2, 3, 4, 5, 6. Now, if you break the bond, I'm going to put this back. Go back to your starting point, which is glucose. Oxygen linked to the number 1 carbon. That is glucose. Now, if you move that bond to the number 2, look, I'm going to try to kind of rotate this a little. I'm not good at this, but I'm going to flatten this out. So if I flatten this from carbon or to the number 2, if it bonds to number 1, you got glucose. If it bonds to number 2, you have fructose. I can tell some of you really aren't getting it, you don't like it. Don't worry about it. It is off the record. I just want to give information. So back on the record, the part you need is that the second reaction is changing glucose 6-phosphate into fructose 6-phosphate. You don't need to worry about how it's done. I mean, it's just not necessary. But glucose is essentially changing into fructose, but again, specifically glucose 6-phosphate changing into fructose 6-phosphate.
Is there a name for that, kind of like a phosphorylation?
No. But the enzyme that does this is isomerase. Isomerase. The accent's on the second syllable, so isomerase. Isomerase is an enzyme that changes the shape of molecules. It doesn't add anything, it doesn't remove anything. It changes the shape. See, in this case, all that really did is move the bond. Nothing else was changed. There was nothing added or removed. The bond moved. Well, that's what isomerase does. It changes the shape of molecules. In this case, by simply moving the oxygen from the number 1 carbon to the number 2. Again, you don't need to remember that. The number 2 reaction, second reaction, isomerase changes the shape of the molecule from glucose 6-phosphate into fructose 6-phosphate. Now, a significant part of this is isomerase would not have acted upon glucose. Glucose would be too stable. You will only do this with glucose 6-phosphate because glucose 6-phosphate is more reactive. It's got phosphate. So isomerase needed the activated glucose. It would not have worked on glucose alone. The activated glucose is glucose 6-phosphate. So the second reaction is changing glucose 6-phosphate into fructose 6-phosphate. The reason is that it frees up the number one carbon. It gets the number one carbon out of the ring. See, with glucose, number one carbon is in the ring. With fructose, number one carbon is outside the ring. So the purpose of the second reaction is to get that number one carbon out of the ring. Again, my term was it frees up the number one carbon. Gets it out of the ring.
So you point at the number one.
I'm sorry.
You point at the number one carbon.
Right there. Now, the obvious question is nobody's asking because you're afraid I'll answer it, is why do we need to get the number one carbon out of the ring? Well, that'll be shown in the next reaction. But is everybody okay with the second reaction? Again, don't worry about the oxygen bond thing. That was just information. But the basic concept, we're changing glucose 6-phosphate into fructose 6-phosphate isomerase reaction. Is everybody okay with that? Okay. The third reaction is another phosphorylation reaction. Remember, phosphorylation is transferring a phosphate group or adding a phosphate group. So this will be another phosphorylation reaction. So once again, we have ATP. Once again, ATP breaks down to ADP. So let's go ahead and check the reaction off. The same thing as before. ATP will break down to form ADP plus the extra phosphate, P sub I, and then plus energy. So same reaction, which means kinase. Kinase transfers phosphate groups. So kinase is transferring a phosphate, once again, this time to fructose 6-phosphate, transferring to the number one carbon. See, the name itself is telling you exactly what you've got. Fructose 1,6-diphosphate. The diphosphate tells you two phosphates, and the 1,6 obviously is telling you where they are.
So there's two phosphates on 1 and 6.
Pure and simple. I don't know if it's simple, but that is what it says.
1 and 6 or only 6?
That's what it says, 1,6. See, remember now, we have two carbons sticking out of the ring. The number one carbon sticks up, number 6 carbon sticks up. That was the reason for the second reaction. We had to get that number one carbon out of the ring because now we can add phosphate to it. The point is, I mentioned this a few minutes ago, carbons in the ring are extremely stable. You're not going to add anything to carbons in the ring. They're just too stable. So in order to add phosphate to that number one carbon, we've got to get it out of the ring. That was why the second reaction. That made fructose that got the carbon out of the ring. Now we can add phosphate to it. So the second kinase reaction is forming fructose 1,6-diphosphate. That tells you two phosphates. The 1 and 6's tell you that you've got a phosphate on the number one carbon and on the number 6. The name tells you. Go ahead. You got a question?
I can't read that name. What's it say?
It just makes it, I promise you, a lot easier. reaction, another kinase reaction, another phosphorylation reaction. But this one is not activation. The first one was, the first kinase reaction was activation. This one is not. The molecule has already been activated. You don't need to activate it again. So the purpose for the second phosphorylation is symmetry. Symmetry.
The reaction is for symmetry.
Now, symmetry means you have a phosphate on both sides. You have a phosphate on the number 1 carbon, a phosphate on the number 6 carbon. That's your symmetry. The molecule is balanced. There's a phosphate on each side. So nothing to do with activation. This is purely for location of your phosphates. One on the number 1 carbon, one on the number 6 carbon. So you have one on both sides, or on each side, I guess. And that's your symmetry. Symmetry means balanced. Any questions on that? Again, always just ask yourself, could you explain this to somebody else? Now, I realize you've got to go home and look at it and all that, of course. But is there any part of this so far that really just doesn't make sense to you? If it doesn't make